Hello everyone, I'm Nu from Tongji University in China. Today I will present our paper, Adaptive and Efficient GPU Time Sharing for High-Parameter Tuning in Cloud. As we know, the accuracy of machine learning training is closely correlated with the model high parameters, such as learning rate, batch size, and wear decay. HPT chooses a set of optimal high parameters for a learning algorithm. A generic framework of HPT system mainly consists of four modules. The first is hyperparameter generation, the second is hyperparameter evaluation, the third is job execution, and the last one is resource provisioning. However, the current resource provisioning approaches have some bottlenecks that fall short of adaptively adjusting resources with the upward trends of HPT accuracy, resulting in low GPU utilization or HPT accuracy. Here is a figure showing different upward trends of HPT accuracy curves with the number of iterations. In general, there are three accuracy levels: high variance, low variance, and no variance. We observed that job A and job C quickly improve the accuracy at the beginning of training and then become stagnant in accuracy improvement, while job B can continuously improve the accuracy until reaching a high level. Further training those high parameters with a low or no variance reduces the GPU efficiency. To better illustrate our idea, here we show you an example. This figure presents three HPT resource provisioning approaches. The naive approach selects the set with the highest accuracy after all iterations of training have been completed for multiple sets of high parameters. In earlier stopping approach, multiple rounds of comparisons are performed during training. HPT job with the low accuracy are terminated in each round, freeing up resources for allocation to other jobs. The GPU time sharing allows one GPU be shared by multiple jobs with time slicing. The naive approach takes the longest time for the total of 20 seconds. However, it can return with accurate results. The earlier stopping approach takes the shortest time for the total of 12 seconds. It reduces the job completion time. However, it mistakenly stops job B earlier, resulting in inaccurate results. Fortunately, we observe that the GPU time sharing takes total of 16 seconds to obtain accurate results. It reduces the job completion time compared to the naive approach and improves the HPT accuracy compared to the earlier stopping approach. We can thus take advantage of the GPU time sharing to design a better resource provisioning strategy for HPT. There are also dynamic resource provisioning approaches using checkpointing for machine learning training. However, those approaches are inefficient for HPT due to high overhead of context switching and job restarting. Our study shows that when model VGG19 uses a DAM optimizer, the checkpointing file reaches 1.7 GB and the overhead reaches 59.2 seconds. So we proposed our disk. The core idea of disk is that adaptively adjusting the size of GPU time slice for different HPT jobs based on their upward trends of accuracy at runtime and avoiding memory overflow of the GPU due to time sharing. It's non-trivial to achieve this idea, which requires tackling the following challenges: measuring the upward trend of accuracy, selecting jobs, allocating resources, ensuring that the total GPU memory usage does not exceed the GPU memory budget, as shown in the bottom figure. When the time slice is switched from HPT job A to job B, the interactive training of job A is not terminated. The memory occupied by job A still remains in the memory, which could cause the memory usage of job B to exceed the GPU memory budget, resulting in the memory overflow and even system crash. The last is improving memory utilization. An existing solution to the memory overflow problem is to share the GPU according to the peak memory usage of multiple jobs, although it ensures that the memory budget is not exceeded even if multiple memory peaks overlap. The solution can result in low average memory utilization. To solve these challenges, DISC proposed potential-aware GPU adaptive scaling and GPU temporal and spatial memory sharing. Here is an overview of DISC. We implemented DISC based on the CRD upon the Kubeflow and Kubernetes ecosystems, which is designed as a service to provide unified GPU time-sharing access to HPT jobs. Disk is designed in a hierarchical architecture including the local runtime and the central manager. The local runtime includes the adaptive scaler that dynamically adjusts the size of GPU time slices according to the variance of the upward trend of accuracy at runtime, and memory manager, a GPU memory management unit that handles the memory usage requirements of HPT jobs. The central manager includes the cluster scheduler driven by memory usage patterns and the cluster status module for maintenance of cluster resources and HPT jobs information. Now we talk about the potential-aware GPU adaptive scaling. First, we illustrate the potential of HPT jobs. The potential of an HPT job at the current moment is the slope of the line collecting the current point and the starting point in the accuracy curve, which contains both accuracy and temporal information that can clearly describe the upward trend of accuracy. DISC can leverage the potential variance of accuracy to adaptively adjust the size of GPU time slices occupied by HPT jobs on the fly. The size of GPU time slice of an HPT job with low or no potential is reduced, and that with high potential is increased. Next, we illustrate the FAIR multi-armed bandit for HPT. DISC models the GPU adaptive scaling as a FAIR multi-armed bandit using the Nash social welfare. The Nash social welfare considers that the resource allocation to multiple social agents should aim at maximizing the weighted product of the reward of each agent. The weight represents the proportion of resource allocated to agent. The agent with a large reward will be allocated with a large weight. Maximizing the weighted product of the reward of each agent reflects the fairness of resource allocation. DISC views HPT jobs as a multi-armed bandit and the potential as the reward of the arm, and the process of selecting the arm as selecting the HPT job to use the GPU. DISC defines the total reward of the FAIR multi-armed bandit for HPT jobs as HPT NSW. Now it's time for problem formulation. We want to make the value of the cumulative regret as small as possible with several constraints. The cumulative regret is the difference between the total theoretical reward expectation and the actual value after the multiple selecting rounds. These constraints are quite obvious. For example, the termination condition of an HPT job is the potential speedup of the current moment compared to the previous moment decreases to a certain threshold. Based on the modeling, we designed our heuristic algorithm by leveraging upper confidence bound, and here is the pseudocode of NSW-based upper confidence bound for HPT. The theory of upper confidence bound considers that the reward of an arm lies within the interval. Mu and sigma are the expectation and standard deviation respectively. The standard deviation responds to the degree of volatility of the expected reward. The parameter data plays a balancing role, regulating the risk of reward uncertainty due to the standard deviation. In each round, the upper bound of the confidence interval is chosen, indicating the desire to take high risks for obtaining a high reward. According to the confidence inequality, disk defines the standard deviation estimate. The heuristic algorithm combines the standard deviation estimate of the potential and the NSW of the HPT jobs to maximize the upper confidence bound as an estimate of the resource proportion parameter. The algorithm is divided into two parts: new job joining and GPU adaptive scaling. Now we talk about the GPU memory, temporal, and spatial sharing. First, we illustrate the memory usage by the top left figure. Memory usage of an HPT job consists of ephemeral memory and persistent memory. The occupation time of ephemeral memory during one iteration of training is referred to as burst time. The ephemeral memory accounts for the vast majority of the overall memory usage. The persistent memory contains the model parameters, the data needed for one iteration of training, and the CUDA context required for the CUDA program to be executed. The bottom left table lists the CUDA context overhead for different CUDA, PyTorch versions, and GPU types. The right figure describes the ephemeral and persistent memory usages for 8 machine learning models with different batch sizes. Based on the memory usage, disk proposed the time-slice earlier release mechanism. The persistent memory of jobs reside in the GPU memory space at the same time to ensure the minimum memory requirement for job execution. Before each iteration of training, disk determines whether the time quarter of a job can satisfy the burst time occupied by the ephemeral memory. Training can only start when the condition is met. Based on the time-slice earlier release mechanism, only one job occupies the ephemeral memory at any given time. As a result, disk can support jobs with large batch size to improve memory utilization. Specifically, disk designs a relaxed pack scheduling policy. It maximizes the sum of persistent memory and the maximum of ephemeral memory for multiple jobs. Disk leverages a bin pack algorithm to prioritize the job so as to minimize the remaining memory based on the ephemeral and persistent memory requirements for scheduling. Here is the pseudocode of GPU memory, temporal, and spatial sharing, which has time-slice earlier release mechanism and relaxed pack scheduling. We evaluated our disk on 16 virtual machines in the private cloud managed by Kubernetes. In all HPT jobs, the hyperparameters to be tuned are learning rate, batch size, and weight decay generated by random search. We experimented with a publicly available trace of DNN training workloads at Microsoft. 7 representative machine learning models are selected from GitHub together with public datasets which are summarized in the table. We used PyTorch as the training framework. We evaluated our disk using 3 metrics. The first is the average job completion time. The second is the max span that measures the completion time of multiple HPT jobs. The third is the validation accuracy of HPT jobs. In the evaluation of resource provisioning, disk can improve the average JCT by 1.15 and 0.82 respectively compared with the naive and earlier stopping approaches in the top left figure. The max span is also reduced by 1.12 and 0.86 respectively. The top right figure shows that the average density of disk is in between those of the other two approaches in the CDF. As shown in the bottom left figure, we used Vining plots with the box lines to measure the statistics of accuracy of multiple HPT jobs. The accuracy of the trace by the naive approach concentrates around 0.65 with the median 0.61. Furthermore, the accuracy due to the earlier stopping approach mainly concentrates around 0.35 with the median of 0.36. The PDF of disk is close to that of the naive approach, while the median 0.57 is slightly lower than that of the naive approach. In the evaluation of GPU memory sharing, disk can increase the maximum batch size by more than 2 times in all 11 settings, compared to the peak usage sharing that shares the GPU according to the peak memory usage of multiple jobs. In disk, only the persistent memory is occupied at the same time, and the ephemeral memory is occupied at a completely staggered time. In other words, only one job occupies the ephemeral memory at any given time, which can support jobs with large batch size. As a result, the memory utilization is significantly improved. We also compared the relaxed pack scheduling policy in disk with 3 popular scheduling policies: FIFO, SRTF, and BIMPACK. The left table shows the trace-based experimental results on the completion time of the 4 scheduling policies. The max span of disk is the smallest. Since disk adopts a relaxed BIMPACK strategy, the memory utilization is higher. As a result, the average queuing time of disk is closer to the smallest one of SRTF. The right figure shows the trace-based experimental results on the accuracy. Disk has the biggest median accuracy compared to other policies. The sensitivity analysis focuses on 2 parameters: adaptive scaling time window size and potential speedup threshold. The larger the time window is, the closer disk is to the naive approach. However, the median accuracy does not increase but gradually converges to 0.6. Therefore, disk chooses 10 minutes as the default size of time window. Disk also empirically selects -2 multiplied by 10 to the power of -5 as the default potential speedup threshold, which can reduce the job completion time while maximizing the HPT accuracy. The overhead is mainly due to obtaining potential dynamics of accuracy of HPT jobs from the database at runtime. We trained ResNet 50 for 100 minutes and found that the total overhead is less than 2%. In summary, we have introduced the disk, an adaptive and efficient GPU time sharing for HPT services. Disk introduced potential-aware GPU adaptive scaling that adjusts the GPU time slices according to the potential dynamics of accuracy of HPT jobs on the fly. And disk proposed GPU temporal and spatial memory sharing that improves memory utilization while avoids GPU memory overflow due to time sharing. We adopted a subset of Microsoft Trace with public datasets to conduct evaluation. Experimental results show that disk can improve the average job completion time by 1.15 compared to the naive approach, and the HPT accuracy by 1.58 compared to earlier stopping approach. That's all, and thank you.